Good afternoon, everyone. My name is Zhuang. I'm a PhD student from Southern University of Science and Technology. It's my pleasure to participate in IEEE Sensor Conference and present a paper titled Pulse Heating Combined with Machine Learning for Enhanced Gas Identification and Concentration Detection with Most Gas Sensor. So my presentation will be divided into 4 parts. First, I will provide some background information. As we know, machine learning has improved various sensors performance, such as image sensors, pressure sensors, tactile sensors, gas sensor. There are various types of gas sensors, of which metal oxide gas sensor are popular due to its good sensitivity, fast response, low cost, and other characteristics. So, however, in critical application, there are still many challenges associated with most gas sensor. For example, over time, the baseline of the gas sensor drifts, leading to a decrease in gas sensing accuracy. Gas sensor sensing materials need to operate at high temperature, result in high power consumption. During the gas sensing process, oxygen molecules are absorbed onto the sensor surface and get ionized by capturing electrons near the semiconductor surface. Then the target gas molecules react with oxygen ions, make it challenging to distinguish between different gas types during this process. Consequently, most gas sensors suffer from the poor selectivity. For those challenges, they all has a traditional co-response strategies. For example, calibration was used to overcome the baseline drifts. We can decrease power consumption by improving fabrication process. For poor selectivity, sensor array will be a good choice, but those traditional strategies are complicated to operate. So in our research, we will propose the use of the pulse heating and machine learning method to address these issues. Next, I will talk about pulse heating and machine learning. So figures 1 display a schematic diagram of the gas sensor test. So we applied a pulse signal as shown in figure 2A to the sensor's heating electrode. Then we collect test signal using a data acquisition card. The figure 2B and 2C illustrate that the most gas sensor signals drift over time. That's the drift. The pulse signals exhibit a similar response. Similar response type like figure 2C. So after normalization, we discovered that the power signals exhibit a repeatable response. So I think power signals hold the promise for improving the baseline drift in gas sensor. Yeah. So furthermore, we obtained the power signals for 3 different gas types and concentrations. We noticed different gas type and the concentration has a different pulse response pattern. But it's still hard to obtain specific information about gas type and concentration information directly from the pulse signals. So therefore, machine learning is introduced here to learn the pulse signals features for concentration estimation and gas type identification. So here I will introduce 3 machine learning approach on top of two models. First is a GRU with a double loss function. Power signals we've seen previous is a typical timing date. GRU is good at process timing dates. So the figure B shows a GRU structure, and then the figure A shows the general structure of the GRU with double loss function. It contains four GRU layers and the three fully connected layers. The power signals are molded in such a way that gas type and the concentration information can be directly obtained. So those are the hyperparameters of this model. So next model I will introduce is model staking. It has two approach. One is a cascade model. Another is a model selection. For cascade model, we initially use a design tree to get a classification result, and then we add the results to the original input as a new input to bring to the MLP to get the regression output. For model selection, it has the same process in a classification phase. Then we choose a specific model we trained before for a specific gas type. Then we can get its regression output. So the figure, this figure is the design tree algorithm structure. It has five dips, and the power signal can be modeled by this way to get a gas type, and then the figure 5 is MLP algorithm structure. So the input side is 580. The fully connected layer of the MLP have no number 300 135 respectively. Then we can get the regression result of concentration. So this table shows the model evaluation result of those three approach, and the comparison group individual MLP. So we can see they all has a better performance than individual MLP model. So figure 1 represent identification MLP models prediction and the truth. Then figure B means GRU's regression result, and the figure C is cascade model regression result, and D to F display the model selection regression result for three gas, ethanol, acetone, and formaldehyde. Yeah. So the double loss function of a multitasking approach with single model, but it requires carefully management the weight distribution between two tasks, so for model staking, the cascade mode has a smaller model size but low accuracy, where the model selection offers a better accuracy with a larger model size. So we can choose appropriate model based on the situation. Yeah. So in summary, we propose pulse heating combined with machine learning to enhance gas type identification and concentration regression. We introduced the three approaches on top of two models, though they all have some disadvantage and advantage. All of them perform the task of the classification and the regression effectively. So by using pulse heating, we can get lower power consumption, dynamic response process, and we can use machine learning to get a stable and accurate gas response. Yeah. So that's all about my presentation. So thank you.